Welcome to today's Explainer. We're going to be looking at the hidden physics of semiconductors today. But don't worry, we're not doing dry textbook theory here. Instead, we're going to solve a real-world engineering mystery together. The case of a mysteriously draining battery. It's honestly the perfect way to see how the invisible atomic world completely controls the gadgets you and I rely on every single day.
So let's dive right into a diagnostic scenario that honestly could happen to any of us. Meet Raju. He recently moved into a new house and, lucky him, he finds a leftover solar panel just sitting up on the roof. So he goes out, buys a brand new battery, and wires the whole thing up to store all that free daytime energy. Fast forward a few days, there's a nighttime blackout. Raju goes to use his stored power and nothing. The battery is entirely dead. So what's going on here? Is the brand new battery already faulty, or is the roof panel somehow broken? Time to put on our detective hats alongside Raju. Step 1. He checks the panel during the afternoon sun by hooking a simple light bulb into the circuit. It shines brightly. Okay, so the panel is definitely generating electricity. But later that night, in the pitch dark, he's up on the roof, accidentally touches the solar panel, and realizes it is literally hot to the touch. Now, a solar panel should absolutely not be generating heat in the dark. It turns out the panel isn't absorbing energy at all. The electrical current is actually flowing backwards out of the battery and right back up into the panel.
To understand why this backward flow is happening, we've got to look at a fundamental rule of electricity. Current always flows from high potential to low potential. Think of it exactly like water flowing down a hill. During the day, sunlight hits that panel, right? That creates a massive high potential, pushing the electrical current downhill into the lower potential battery, charging it all up. But what happens at night? The sun vanishes and the solar panel's potential drops literally to zero. Now, that fully charged battery is the one sitting at a high potential, while the panel is at zero. The hill has completely reversed directions, so the battery naturally pushes its stored current backwards, right into the panel. That generates that weird heat and entirely drains Raju's power supply.
So, how do we fix this incredibly frustrating problem? Well, Raju needs to force that electricity onto a strictly one-way street. Enter the absolute hero of our story, the diode. A diode is this brilliant little piece of semiconductor engineering. It conducts electricity seamlessly in one direction, but the split second that current tries to reverse, it instantly transforms into a rigid insulator. No backward flow allowed. Which brings us to section 1, inside the semiconductors, zooming down to the atomic level. To make a diode, you combine two very specific, yet completely neutral materials. On one side, you have the p-type semiconductor. Now, this material relies on something super fascinating called holes, which are literally just missing electrons. And even though they're just empty spaces, they behave exactly like positive charge carriers. Crazy, right? Then on the other side, we have the n-type semiconductor. This one is packed with extra, freely moving electrons that carry a negative charge. But here's a really important thing to keep in mind. If you just have a random chunk of p-type or n-type sitting all on its own on a table, they are absolutely terrible conductors. You could change the voltage on them all day and it does pretty much nothing.
But watch what happens when we squish them together. When you join the p-type and n-type materials, they don't just sit there. Right at the exact border where they touch, the extra electrons from the n-type side actually rush over to fill those empty holes in the p-type side. They keep shifting across the border until they build up this invisible wall of electric charge. This newly formed internal electric field acts as a massive barricade. It gets so incredibly strong that it actively repels any more electrons and holes from crossing over. It effectively creates a total roadblock for any electrical current.
So, how in the world do we get power through a roadblock? Well, we have to overpower it. In engineering, this is called forward bias. To do this, we hook up the p-type side of our diode to a high potential and the n-type side to a low potential. When we do that, we are applying a really strong external electric field that pushes directly against that internal barrier wall we just built. The pressure from these high and low potentials is so intense that the microscopic charge carriers, those electrons and holes, are forced straight through the barricade. The wall literally comes down, and current flows freely and abundantly.
But what happens if the electricity tries to flow backwards? Well, the electrical polarity is flipped, creating what we call reverse bias. Now, instead of fighting against that internal barrier wall, your external electric field actually joins forces with it. The two fields align in the exact same direction. So that electric field wall, it becomes incredibly thick, super strong, and entirely insurmountable. The electrons are facing such massive opposition that they literally cannot move. The result? The current is completely blocked. The door is locked tight. No electricity is getting through. All right, let's look at section 2, the resolution, fixing Raju's solar panel. When engineers use a diode specifically for this exact purpose in a solar setup, they actually call it a blocking diode. By just installing this tiny, super cheap little component directly into the wire that connects the panel to the battery, Raju basically creates an automatic, highly intelligent gateway. Think about it. It requires no switches, no timers, absolutely no manual effort on his part. It just purely relies on the underlying laws of physics to automatically respond to those shifting power dynamics between the solar panel up on the roof and the battery down below. Let's actually watch this diode in action across a full 24-hour cycle to see how cool this is. During the bright, sunny daytime, the solar panel's voltage is super high. This perfectly aligns to put our blocking diode into forward bias. That invisible wall is knocked down, and the battery eagerly charges right up. But the very second the sun goes down, that whole dynamic flips. The battery voltage is now higher than the sleeping solar panel. So, as the battery naturally tries to push its stored electricity backwards, it instantly forces the diode right into reverse bias. That internal wall reinforces itself, acting as a totally impenetrable shield. The backward drain is 100% blocked. So Raju's battery stays perfectly full all night long, totally ready to power the house during the blackout. Problem solved. So, by understanding atomic barriers, Raju's battery drain is permanently solved. But honestly, while we've answered one big mystery today, it leaves us with an incredibly fascinating, lingering question. We know that joining p-type and n-type materials creates all this electrical magic, sure, but how exactly do engineers manufacture these microscopic, invisible holes and extra electrons into solid blocks of material in the first place? Like, how do you build something that conducts using literal empty space? That is a whole different level of semiconductor wizardry, and it's exactly what we're going to explore in our next explainer.